Alright, so we're continuing now with our review of the various functions that are going to come up in our calculus course, Math 1560 at the University of Lethbridge. Next up in the list of functions to consider are the exponential functions. So we're now moving past the sort of basic functions that you can obtain using essentially arithmetic, right? So polynomials, rational functions, these are functions you can build using addition, multiplication, division. Now we're getting into things that are a little bit more complicated, right? So for an exponential function, let's say something like 2 to the power of x, how do you actually define a creature like this? Well, we start by understanding what it means to deal with positive integer powers, right? So when you first learn about exponents in school, you learn about an exponent as kind of repeated multiplication, right? And so you think about something like 2 to the 6th, and you say, okay, so what does that mean? That means you multiply 2 by itself 6 times. Okay, simple enough. 2 times 2 times 2 times 2 times 2. Is that 1, 2, 3, 4, 5, 6 of them, right? And if you want, you can work that out. That comes out to give you 64. Okay, so we can do that. What about integers? Can you move beyond natural numbers? Sure. We know that the integers include the positive numbers, the natural numbers. They also include 0. By default, 2 to the 0 is always defined to be simply 1. Anything to the power of 0 is 1. And then negative exponents, well, negative exponents are essentially defined as reciprocals. So if I wanted to do something like 2 to the minus 3, by definition, that means the same thing as 1 over 2 to the 3, and so I get 1 over 8. Okay, fine. Now, what about if you want to move beyond integers? You want to get to fractions. Well, first of all, how do you deal with reciprocals? Reciprocals we can handle too, because by definition, reciprocals are simply roots, right? So 2 to the 1 over n is the nth root of 2, right? So for example, 2 to the 1/2, that's the square root of 2. Okay? One of the reasons for this is kind of you can make sense of it in terms of laws of exponents. If you multiply this thing by itself n times, you add this exponent to itself n times, and you end up with 2 to the 1, right? So you should expect that an nth root is something that you multiply by itself n times to get back to the original number. Once you get to rationals, well, rationals are defined by kind of combining these two. So if I want to do something like 2 to the p over q, okay, p and q are both integers here. I can either define this as, well, I can do 2 to the p to the power of 1 over q. Again, we're using laws of exponents, which say that if you have a power raised to a power, you should multiply those. And so what this means is that you should take the 2 to the power p, as we did in kind of the first case, and then you take the qth root. Okay, or you could do it the other way around. You could think of it as doing 1 over q and then p, in which case you would first do the qth root of 2, and then you would raise that to the pth power. And of course, these two quantities are equal. So that takes care of rational numbers, but then we want to deal with functions of a real variable. How do you get to the real numbers? Well, the short answer here is that we're kind of doing this via continuity, right? And we haven't really defined what continuity is yet, but the idea is that, once you've got all the rational numbers, there are still certain gaps in the number line that are missing, and the real numbers are what you get when you fill in all of those gaps. And so if you think about, say, graphing 2 to the x, right, once you've plotted all the rational points, there are still certain gaps in the graph, and so you extend to the reals by insisting that the graph should be one solid line, right? The graph is not going to jump around. It's going to be this nice kind of continuous, it's going to go on like that. So that's essentially how you define it for real numbers, at least for this course. Interestingly enough, one common approach in calculus, it's not the approach that we take in our calculus course, but a common approach that some people take is to leave the exponential function until after integration. And surprisingly enough, You can define the logarithm using integrals, and then you can define the exponential function as the inverse of a logarithm. It's an interesting approach to take, but it's not the one that we go after. If you're curious, I can tell you about it at some point in the future. Now, the most common exponential function that we look at is the natural exponential function. We're going to see as we move forward in the course that the reason we like this in calculus is that it has particularly easy derivatives and also integrals. Other exponential functions are much more complicated when it comes to integration. Now, one of the ways that you can kind of think about the exponential function, where it comes up from, and again thinking in terms of integration, is that we're looking for. Here's what it is really. Is you're looking for the exponential function, so that when you graph it, y equals e to the x. You're looking for the one so that when you kind of construct the tangent line at 0. And of course, we'll be talking about how to construct tangent lines later on in the course. So we want the tangent at x equals 0. It turns out that the natural exponential is essentially defined to require that this tangent has slope 1. We'll see later on what the significance of that is for derivatives. So just to give you an idea of what this looks like, we can play around here and look at what the exponential function looks like for different values of the base. So right now I've got a base of 1. You can see the a equals 1 here. Well, that's not a very interesting exponential function, right? Because 1 to any power is still 1. It's a constant function. But I could move it up a little bit, right? So as I move it up, you'll see that if I go to values bigger than 1, you see this classic behavior that you expect for an exponential function. It goes off towards 0 in one direction and it shoots way up in the other direction. You can consider values that are between 0 and 1, and you actually get something that is flipped around if you do it that way. If you consider numbers that are less than 1, that's certainly an option that you have. And so you go off in search of this exponential function. There's 2 to the x. Well, there's 1.91, but 2 to the x is in there somewhere. I'm not going to hit it on the nose. The natural exponential is somewhere around there. Okay, it's 2.71. I don't know if I can get it up. It's tough to get that slider exactly where you want it. Close enough. And if we wanted to, we could probably construct a tangent to this guy. I don't know if I can pull that off. Let's see. I want a tangent line. It might not do it for me. Okay. Oh well. Anyway, I thought I could pull that off, but not with just my pen. I would need my keyboard to get it. So you could try to construct the tangent to that line, and you would see that the tangent to that line would have slope 1. So as you kind of play around with the value, you can see what happens as you move that slider back and forth. Okay. And so somewhere among all these values for the base, there's a certain sweet spot that happens somewhere around 2.7. Where you get an exponential function with particularly nice properties, and that's the natural exponential function. Okay, so we'll see that it's the one to use for this course. Now, for all exponential functions, there are certain properties that they satisfy. These are the so-called laws of exponents. Sometimes you deal with cases where you have two different bases raised to the same power, right? So if you have a power that is being attached to a product or a quotient, you can distribute it across that product or quotient. You do see that come up from time to time. The ones that are most relevant for a particular exponential function are these guys here, 3 through 6, right? So as we said, the way you define, this works for all real numbers, but in particular, this is how we defined integer exponents, negative integer exponents, is you define negative powers as reciprocals, right? We have the rule that if you multiply two two powers with the same base, you should add the exponents. If you divide, you subtract the exponents, and a power raised to a power, you multiply the exponents. So we have these standard laws of exponents. And it's a good idea to kind of get comfortable working with these because you're going to see them coming up quite a bit when we're simplifying various algebraic expressions. They are certainly going to pop up on you. Do a couple of examples here where we're dealing with some numbers, some expressions. So let's say I've got something involving the natural exponential function here, right? So I've got e to various different powers here, and then I've also got this power on the outside. So if I were going to deal with this, I would first deal with that exponent. So using essentially property 6 here, and then combined with 1 and 2, I can say that this is going to equal, well, is going to equal e to the 2x. I guess we'll distribute it first, right? E to the 2x squared, e to the minus x squared over e to the x and then squared. Now I use the rule that I multiply exponents, so this is going to be e to the 4x times e to the minus 2x over e to the 2x. Now let's work up top. I'm multiplying these two powers, so I should add the exponents. 4x minus 2x is 2x. Leaves me with e to the 2x divided by e to the 2x. Well, just 1. Okay, that was not so exciting, was it? Of course, there are other ways we could have simplified. I could have worked inside the brackets first. I could have realized that the thing inside the brackets simplifies to 1, and then 1 squared, of course, is still 1. There's more than one way that you could have tackled this. Here's another example working directly with some numbers and laws of exponents. How would you simplify something like this? 81 over 16, we want to raise it to the power of minus 3 over 4. Well, the first thing we might realize is that 81 is 3 times 3 times 3 times 3 is 3 to the 4th power. 16 is 2 to the 4th power. And we're raising this to the power of minus 3 over 4. Now, the negative exponent says we should take a reciprocal. So this is the same thing as 2 to the 4th over 3 to the 4th raised to the power of 3 over 4. Now I can use property 2 here. I've got a quotient raised to a power. I should distribute that power to the top and the bottom. So 2 to the 4th to the 3/4, and then 3 to the 4th raised to the power 3 over 4. Now I use property 6 here, which says that a power raised to a power, I should multiply exponents. So 4 times 3/4 leaves me with 2 cubed, and the same thing on the bottom, that's 3 cubed, and so 2 cubed is 8, 3 cubed is 27, and I'm done. Alright, that's it for exponential functions. In the next video we'll move on and we'll talk about logarithms.